So if we look at what's going on as we start applying pressure, so we have a rock over here in C, and it's got pore space. We apply more pressure, the pores all close, so now they're effectively little teeny cracks. Apply more pressure, the edges are bowing, it's creating some tension in the middle, but because of the orientations and number of cracks, we're not getting one of those vertical joints forming. Instead, we get a diagonal fracture and then displacement happens. So if we look at a curve of what's going on, at first we have closure of the cracks, then we have some elastic compression, then we have new cracks forming, some of those cracks start connecting, and we have failure. And that relieves all the stress. So that's why this line of increasing stress stops right there when the failure happens. Now, there are two ways to create a brittle fault. We can shear and rupture an intact body of rock. So it was a nice solid rock, lots of stress, it cracks, it breaks, there's displacement. That's a shear brittle fault. Or we can reactivate a previously formed, now weaker surface. A fault can form along a vein. If you have this sturdy rock, it cracks, tension cracks, joints, fractures from an impact, a meteorite strike miles away, volcanic eruption, earthquake, something that cracks the rock. Then no displacement, so it's not a fault. Thousands and millions of years go by, water deposits a mineral in there, calcite, halite, something very water soluble. That mineral is a lot weaker than the rock. Therefore, when you go applying new stresses, is it going to fracture in the sturdy rock, or is it going to fracture in that weaker mineral vein? Of course it's going to fracture in the vein. It's sort of like, trying to glue pieces of rock together with chewing gum, and then you start putting pressure on there. You're not going to break the rock, it's just going to slide where the chewing gum was holding it together. Key thing with the vein is the two surfaces of the rock that were fractured initially are no longer touching each other because the other minerals in there are taking up space. Halite and calcite are quite soft, very low on Mohs hardness scale. That's why they are so weak. We can also have cataclastic flow, or cataclasis. Cataclasis is movement on a fault by a combination of microcracking, frictional sliding, and rotation and transport of grains. So it's, everything's going on at once. I use the marbles under a box analogy. You could also think of corn in a grist mill between the stones. They're getting ground smaller and smaller. They are being destroyed as they grind in there, but they're allowing the stones to roll past each other more easily than they would if there was no corn in there. This is going to result in localized ductile strain, which results in cataclastic flow. Those rocks that are in there move as the fault moves. The area is then a cataclastic shear zone, and as there's more and more movement, the rocks that are in there get ground finer and finer. They can end up as, incredibly fine clay-sized dusty particles.